Hi everyone, we're going to start on slide 36 that deals with half-lives. So we've looked at first order and second order reactions with kinetics. We're still going to look at first order and second order reactions, but now specifically we're going to focus on how half-life has to deal with kinetics. We've talked before, pretty much last year when we went into nuclear chemistry, about what half-life was, and it's ultimately just the time that's required for 1/2 of a reactant to react. So when we think about half-life, we think about that half of a reactant reaches half of its initial value in a certain amount of time. To be more specific and to give some variables with it, let's look at this right here. So it says because A, and remember those are my concentration brackets, so we'll say because the concentration of A at a specific half-life is 1/2 of the original concentration, then we've come up with this symbolic way to represent half-life, and that is just that the concentration of A at some time, and specifically, let's say when it's at its half-life. So instead of just saying the concentration of A, and that T should be in subscript, concentration of A, we'll say at its half-life, so T1/2 equals half, 0.5, of the original concentration. So there's my subscript 0, or we could say concentration of A, and then frequently we call 0 not. So either way that you say it is fine, but 0 is just representing the original amount of A that we had. So the concentration of A at half-life is equal to 1/2 of that original concentration, which should logically make sense to us. Guys, this slide on here kind of looks a little wonky, so let's go just new page. You're just going to have to follow along with me looking at your slide for this one. So let's say that we have a first order process and we want to know about this first order process in terms of its half-life. Now, we've learned before that a first order process has an equation of the natural log of the concentration of A at some specific time during that reaction over the original concentration of A. So I represent that with the 0 because that's telling me that it's the original concentration. That equals a negative K, remember that's my rate constant, times time. So this would be my formula for a first order reaction. We've already talked about that. So we also know from that last slide that the concentration of A at exactly half, at half-life, is equal to 0.5 times that original concentration. So if here, let's look here, if this is where my half-life is, let's say that that is the concentration of A at half-life, then let's substitute in our 0.5 of that original over here for this particular variable. So if I do that, that would give me the natural log of 0.5 times the concentration of that original A over the concentration of A originally. Okay, so, let's keep going, equals a negative KT. Okay, so ultimately I have the concentration of A originally over the concentration of A originally. So because of that, it's like those two are canceled out. So let's simplify then this once more. The natural log of 0.5 equals a negative K times T. Well, in our calculators, we could plug in the natural log of 0.5. If we do that, we would get negative 0.693 equals a negative K times T. And remember, can make this consistent, guys, too. I should say that this is it. This is half-life. So this is T, we should say this T subscript 1/2. Okay, so let's say I want to know then how can I solve for half-life? How do I know how much time it's going to take for specifically my original A concentration to reduce down in a specific amount of time? Well, I could say then that to solve for this, I can divide both sides by that negative K. If I do that, I have two negatives. So I have a negative 0.693 over a negative K. Negative over negative is going to cancel out, make it positive. So ultimately, half-life is equal to 0.693 over K. Remember that K is our rate constant. So if we're looking at our formula to find half-life based on a first order process, then for us we can see that the half-life does not depend on that original concentration at all. And I know that because nowhere in the formula, my half-life formula of 0.693 over K, do I have that variable of the concentration of A originally. I don't see this. So that's why I can say that in the first order process, half-life does not depend on that original concentration. Guys, again, this slide, little weird looking, so I'm gonna make a new page so that way you'll just, again, have to follow along for a second order process. Okay, so for a second order process, we know that second order has that relationship of 1 over the concentration of A, and we'll say that that is here at a half-life, or half the time, equals my K times half-life plus 1 over that original concentration of A, and that, guys, should be a 1 on top of that. So let me just... maybe I can't erase it. Just know that that's 1 over concentration of A originally. Okay, so again, we said that, let's go back to us saying that our concentration of A at half-life is equal to 0.5, that original concentration of A. So let's substitute this in again for our concentration of A at half-life. So if I do that, I'm going to get 1 over 0.5 times that original concentration of A. That equals K times the half-life plus 1 over the original concentration of A. Okay, well now I want to simplify this down as much as possible. 1 over 0.5, if I'm looking at that, I have 1 over 0.5, well, that would just be 2. So let's simplify this. 2 over the original concentration of A equals K times the half-life plus 1 over the original concentration of A. Okay, well, again, my goal is to find what half-life would equal. So half-life is going to equal some variables, and that's what we want to try to get to. So I need to simplify this yet again. If I subtract this quantity on both sides, then ultimately I'm going to be doing 2 over the original concentration of A minus 1 over the original concentration of A, which should just give us then 1 over original concentration of A equals K times half-life. So hopefully we can all agree on that. If I simplify that down even further, I want just this half-life by itself. So that means I have to divide both sides by K. So to do that, I would get half-life is equaling 1 over K times concentration of A at its original concentration. So in the second order process, I see that half-life is dependent on that original concentration of A. So the biggest difference that we should know that for a first order process in terms of half-life, that the half-life is equal to 0.693 over K. That's something we should know, and that's for a first order. And then for a second order, we should know that half-life is equal to 1 over K times the original concentration of A. So in a first order half-life problem, we know that the original concentration doesn't really matter in terms of half-life when we're trying to calculate that. But in a second order process, the half-life is dependent on that original concentration. Okay, so let's look at an example. Again, we've looked at butyl chloride and how it can react with water to form butyl alcohol. We've looked at this one a few times, so let's just be consistent and look at it again. Let's say that we have the reaction of butyl chloride with water, and let's say it's a first order reaction. It says use the figure next to the side here, to the right, to estimate the half-life for this reaction. So that's part A. And then part B says use the half-life that we found to calculate the rate constant. Okay, so how am I going to figure out what the half-life is based on this graph over here? We know that the initial concentration then, or the original concentration of butyl chloride is going to be up here at where time is equal to 0. So if my time is equal to 0, I can look up here, my concentration of butyl chloride is 0.100 molar. Now, if a half-life occurs, we know then that in a specific amount of time, the concentration should go down by a half. So that means if I'm starting off originally with 0.1 molar, then ultimately at half-life, that concentration must go down to here. 0.05 molar, because that would be half of the concentration. So if I move my line over here and I look at the graph at 0.5 molar, that's a really bad line, guys. I apologize. We're probably at about eyeballing this instead of following my line because that's terrible. If I'm looking at my line is probably at around 340 seconds. So our half-life then would be 340 seconds. And we know that just because originally I'm starting off with 0.1. At half-life, I have to be half of that original concentration, which would be 0.05 molar. I look at my line, that red slope here, and then, or my red curve, and then I can follow down to where the time is, and should probably be roughly around 340 seconds. So now that we know the half-life, they want us to calculate the rate constant. So I'm trying to find K. What is K? Now, I know that this is a first order reaction. So because I know that, I know also how to find half-life. And that is half-life equals 0.693 over K. Well, we know half-life, we just found that from our graph, 340 seconds. That equals 0.693 over K. So then if I simplify this down, try to solve for K, ultimately I'll end up having 0.693 divided by 340 seconds is what K will end up giving me. So if I do that, let's erase that. Then we would get K equaling 0.0020. And then what are my units here? Because ultimately what will happen, we multiplied both sides here by K. Now K is canceled out. So that left me with 340 seconds times K equals 0.693. So then remember we said to get K, we're going to divide then by 340 seconds on both sides. So K is equal to 0.693 over 340 seconds. So that means this should be a per second, or seconds to the -1. So we could have written it like that. Or you could have written it 0.0020 per seconds. Either one works out just fine. So we've talked before about temperature and rate, but again, generally as temperature increases, we also know that reaction rate will do the same. They are directly related. And based on our POGL, we know that they're directly related because as we increase temperature, the kinetic energy is increasing. And so because kinetic energy is increasing, we also can think about pressure increasing. So remember, pressure and temperature are directly related because of Gay-Lussac's law. And we also know that as temperature increases, as pressure increases, so does collisions, or so do collisions. So because collisions are increasing, we have more of a chance to have a higher reaction rate. So if we look over to the side here, if we break open, or if we break a glow stick to try to activate that chemiluminescence reaction to happen, we can see here that in the cold water, it doesn't look nearly as bright as what it looks like when it's in hot water. And that's just because the temperature can increase that reaction rate. They're able to collide more, thus increasing how fast the reaction can proceed. So we know that in a chemical reaction, bonds are broken and new bonds are formed. And ultimately, molecules can only react with one another if they collide into each other. So we call this the collision model or a collision theory. We saw this also in our POGL. We know that reaction rates are going to be affected by concentration, and we know they're affected by temperature, but they're affected by temperature and concentration because if those things are high, then the amount of collisions that we have are going to also be increased. So reaction rate can go up. The collision model is based on the kinetic molecular theory. So we've heard of this already in kinetic molecular theory, and it's just a basis from that. And it's accounting for both reaction rate based on concentration and reaction rate based on temperature. So the greater the number of collisions, we know the greater the reaction rate. For a reaction to occur, we need more than just a collision though. So collisions are great. It doesn't mean every time molecules collide with one another that we're going to have a reaction. So molecules have to collide what we would say correctly. They have to collide with a specific orientation, and they also have to collide with enough energy to cause bonds to break, and then furthermore to have then bonds form. So we can call that the orientation factor. Only a very small amount of collisions will usually lead to a reaction. So in most reactions, molecules must be oriented in a certain way, like we said, during collisions for a reaction to occur. The relative orientations of these molecules then, during the collisions, are going to determine whether the atoms are in a suitable position to form new bonds. So in this picture here below, I can see that they're showing that the green is representing Cl. So let's say green equals Cl. Red is going to represent nitrogen, and blue is going to represent oxygen. Okay, so let's actually write a reaction for this too. I don't like that there's not a reaction given. So here we have Cl plus NOCl. And when those two react, we should get nitrogen monoxide and chlorine. Okay, so this is the reaction that we're focusing on. Chlorine, so we have a chlorine plus NOCl should react to form NO plus Cl2. That's our goal, is to see those products. So ultimately, here's my chlorine atom, and I want that chlorine atom to react with or collide with another chlorine atom. or at least another chlorine that would be attached to that molecule. So in this case, it happens. There's an effective collision because this chlorine has now collided in a proper orientation with this chlorine. So because of that, I'm going to make my chlorine and then my nitrogen monoxide. If I'm looking down here below, let's say that in this case, chlorine is going to collide now with the nitrogen. In my products, I'm not trying to make a nitrogen chloride bond. So because of this ineffective collision, ultimately nothing is going to happen at all. Bonds aren't broken. This chlorine is now going to move on to collide with something else, such as this molecule is now going to move on to collide with something else. So like we said in the last slide, that orientation for collisions is super important. It's also important about a certain type of energy that we have to have for a reaction to happen or for a reaction to proceed. So this minimum amount of energy required for a reaction is what we call the activation energy. And we will symbolize activation energy with a capital E and then subscript A to represent that it's activation energy. Now, the person that's most responsible for activation energy is some guy that we talked about last year with acids and bases, and that's Arrhenius. Arrhenius said that molecules needed a certain amount of energy to react. So ultimately, we're thinking, or I should say he was thinking at the time, where does this energy come from? Our kinetic molecular theory, if we go back to that, tells us that we get this energy from the kinetic energies of colliding molecules. So we have to have collisions to get this type of energy. This kinetic energy is used to stretch or bend and ultimately break bonds. And because of this energy, that's leading us to our chemical reaction. And we can think about that also if we're relating kinetic energy with potential energy, in that the kinetic energy is changing the potential energy of the compounds. So if the molecules are moving too slowly, then ultimately those molecules are just going to bounce off each other and those bonds won't be broken at all. So we have to have a certain amount of energy for a reaction to happen, and that energy is what we will call activation energy. So there's a good analogy that your textbook uses, and that's just as a ball cannot get over a hill if it does not roll up the hill with enough energy. So if I'm not going to apply enough energy to the golf ball here to roll up the hill, I'm not going to be able to get that hole in one. Same kind of analogy with that a reaction can't occur unless a molecule will possess a certain amount of energy, a minimum amount of energy to get over what we can call the activation energy barrier. So if I'm looking at my golf analogy here, this hill at the very top would be that activation energy barrier. Okay, so we're going to get into something called reaction coordinate diagrams, and these are just really for us to kind of see what's going on in terms of when we have a collision and comparing that with activation energy. So it's really helpful for us to visualize how energy is changing during a reaction or during such types of collisions with this reaction coordinate diagram. So specifically, we're going to look at something. We're going to look at methyl isonitrile. In methyl isonitrile, we see that in this compound, my nitrogen is here in the center, and then I have my carbon and then this CH3 group over to each side. Ultimately, what's going to happen is, if I'm going to sneak over here and look at my product side, my carbon is now going to be that central atom, and it's going to be attached to that CH3 group, and then nitrogen is going to be my other ligand, or that other end. So ultimately what we're doing is just a little carbon-nitrogen switcheroo. So we're breaking this nitrogen-carbon bond, and now I'm going to form this carbon-carbon bond over here. So let's look at this reaction coordinate diagram. So I have my methyl isonitrile, and ultimately energy is going to be applied somehow I'm going to have my methyl isonitrile. This is going to start to bend. And once I've got enough energy, what do I see is happening here? This is called the activated complex is going to form. This is what we're going to call our intermediate step. So in this particular reaction, my CH3 is going to break apart from my carbon-nitrogen triple bond. And I see that here. So this is where I've reached my activation energy and I've broken a bond. So I've reached enough energy to break bonds now. So this is my activated complex, or remember we have said also that we can think about this as the intermediate. We've heard that term before as well. So as now I've broken this, carbon and this carbon can now come together and form. And remember when we said that as we're forming those bonds, then we're releasing some certain amount of energy. So now that we have formed this will start to straighten out, and I now have my new compound down here below, because this is just what's happening as the reaction is progressing. Okay, so we're going to look quite a bit at these reaction coordinate diagrams. So this is just introducing them. But the diagram is showing us the energy of the reactants and the energy of the products. And to do that, we're going to look at something that's called delta E, or change in energy. Now we can see in the reaction coordinate diagram that we actually have two different types of energy that are shown in this figure. We have E sub A, which we know is activation energy. And then we have our delta E, which we just said is the energy of the reactants and the products. So the difference between the energy of the starting molecule, so there's my isomethylnitrile, or my methyl isonitrile, sorry. So the difference between the energy of the starting molecule, so here's my starting molecule, there's the energy that it has, and the highest point along the path, that's where I can find my activation energy. So where I'm starting, the energy that I have to start off with, to the highest point, that's where I can know my activation energy is. But then how would I find my change in energy? Well, change in energy for a reaction is just going to be the difference in where my products are to where my reactants are. Now in this case, this particular reaction is exothermic because the graph shows that the products have a lower energy than the reactants. So that means we must have released some amount of energy. If your products have a higher amount of energy than your reactants do, then that's going to be endothermic. So remember that a reaction is exothermic if we're looking at a reaction coordinate diagram. A reaction is exothermic if the products have a lower energy than the reactants. And it's endothermic if the products have a higher energy than the reactants. The energy change for the reaction really has no effect on the reaction rate. So this is just something that we look at to determine if a reaction is endothermic or exothermic. Now, the high point on our diagram, right there, where our activated complex forms or where our intermediate is happening, we have a specific name for that, and that's called the transition state. So that highest point on my diagram, that minimum activation energy, we just call that transition state. The species that's present at the transition state, like we said, is just called the activated complex, or you will also hear it as the intermediate. The energy gap, again, between the reactants and this activated complex is just that activation energy, which we show as E sub A. Okay, so we'll continue on. Actually, no, you'll have your lab tomorrow, and then I'll have another blog video that's posted tomorrow after school, and that will be covering maybe like 9 or 10 slides. And then the next day, we may kind of finish up chapter 14, because that POGL, I think, and going over that in class really took care of understanding what kinetics are. I think you guys have a good idea about those. Thursday in class, we're going to do kind of a lab setup with practice, very short practice FRQ questions, and something new. We'll kind of see how that works out. So if you guys have questions on this, post on your blog, email me. If not, then I will see you for lab tomorrow. Have a wonderful day. Bye.